Example 179. At the 1% significance level, test the claim that drinking habits and congestive heart failure are independent events. Okay, so when we look at the statement, test the claim indicates it's a hypothesis test, and then the fact that it talks about two categories being independent tells me it's the chi-squared test of independence, or in other words, it's the chi-squared procedure for testing to see if two categorical probabilities are independent. Alright, so what we want to do here is to look at the first thing, which is the HO and HA. And the first thing we want to recognize is that for this procedure, we always have the same null hypothesis and the same alternative hypothesis. So I've gone ahead and just written it in here. And the null hypothesis is always that the two categories are independent, and the alternative is always that the categories are dependent. So that's the logic of the procedure. It's always that the null, or the status quo hypothesis, is that the two things are independent versus the two things are dependent. You could, of course, fill in what specific categories you're referring to. In this case, we're talking about alcohol consumption and congestive heart failure, and we're saying they're independent in the null, and they're dependent or related in the alternative. Okay, so let's look at the table of data. What I've done here is just taken what they gave us, and I included the totals that they provided at the bottom, and I included now the row totals, so I went ahead and added all these numbers across and got the total 281. I did the same here, got 1632, and then I added up all the data to get the grand total of 1,913. Now, after we do our hypotheses, we normally talk about our data step. So in the data step for these chi-squared procedures, what we're doing is finding the expected values for the cells. So this is what we observed for this category. For people in the abstainer group who had congestive heart failure, out of the 1,913 people in the study, 146 of them were in this category. And so what we want to do is to figure out what did we expect to have happen here if we assume the two categories are independent or unrelated. If they're unrelated, if congestive heart failure and alcohol are not connected in any way, then we would expect how many people to land in this cell out of 1,913. Well, basically that's going to be based on something. It's going to be based on essentially the sample size. So expected value here for a particular cell, let's say the IJ cell, that expected value is going to be based on essentially the sample size times the probability, so the probability of being in the cell, right? Of being in the cell. That's essentially the logic of the expected value. But the question is, how do you figure out this probability of being in the cell? Well, if we assume independence, it's just the probability that somebody is an abstainer for the first cell here, for example. So let's take, for example, 1, 1, or expected value 1, 1. What does 1, 1 mean? That means the expected value for the cell in the first row and the first column. That's here, the abstainer and congestive heart failure yes position, right? So what's the expected value for that? Well, it would essentially be the sample size, n, times, and it would be the probability that you're an abstainer, so probability of being an abstainer, times the probability that you have congestive heart failure. So I'll say congestive heart failure, yes. That would be the two probabilities multiplied times the sample size will end up telling you how many people we should have in the cell. So the question is, do we know these probabilities? Well, we don't know them precisely, but we have an estimate of them based on the data we collected, right? So we know the probability somebody's an abstainer, approximately it would be the number of abstainers divided by the grand total. The probability somebody has congestive heart failure would be the number of congestive heart failure people in the study over the total, and then we'd multiply by the grand total. When you simplify that expression, what you're going to end up seeing is that two of the grand totals will cancel out, leaving just one at the bottom, and you're going to end up having the following formula. It's going to basically end up being the row total times the column total. And all of that will be divided by n, which is the grand total. So the grand total. And of course here we'd say the ith row total and the jth column total, because this is for the ith j position. In this case it would be the 1, 1 position, right? Because we're doing the expected value for the first cell, or sorry, for the cell in the first row, first column. Okay, so with that in mind, let's go ahead and fill that in. What is the row total for the first row? Well, it'd be 281, right? So for the expected value for the first, the cell, sorry, in the first row, first column, it's going to end up being the row total of 281 times the column total for the first column, 896, right? divided by the grand total, which is 1913. Let's see what that gives us approximately. So we'll end up having 281 times 896 divided by 1913. And when you're done, you get 131.61 if you use 2 decimal places, right? So 131.61, that's approximately correct. Okay, so that's the expected value for the cell in the first row, first column. What about this position? What would this position be? It'd be the first row, second column. So let's figure out what that is. What's the expected value for the first row, second column? Well, again, we'd have the row total, but it would be for the first row. So what's the row total for the first row? 281. What is the column total for the second column? That would be 696. Divided by the grand total, which is 1913. And again, what is that approximately? Well, 281 times 696 divided by 1913. And you get 102.24. So that's this position here, 102.24. Now you have the expected value for that cell. And we need to continue all the way down here, all the way across until we finish all of them. Let's do the last one. So we'll just say kind of here, dot, 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 dot. What do we get for the last cell? How about the expected value for, what's the name of this cell? Well, it would be in the second row. We always put the row first. Second row. And it'd be the third column. 1, 2, 3, the third column over. And then to figure out the formula, it would be the row total for the second row. That row total is 1632 times the column total for the third column. That would be 321. Divided by the grand total, which is 1913. Alright, let's plug that in, see what we get. 1632 times 321 divided by 1913. And when we do that, we get approximately 273.85. So 273.85, 273.85. Now for these other positions, I've already done those, so let's work those out here, or just fill them in. We have 47.15. For this position, we have 593.76, and for this last one, we have 764.39. Okay, so we worked out these three together. You work out these three on your own, see if they check and match up with what I found. Okay, so once you have the expected values, what you're going to do then is to figure out the test stat. So after the data step, we usually do the test stat. So remember the test stat formula, so I'm just going to write it out here. The test stat formula for a chi-squared test statistic is this chi-squared formula where we do the summation of the observed minus the expected squared over the expected, right? So we have some notation with the IJ subscripts, but I'm going to leave that out because some people find that confusing. And what I'm going to do is just fill in the fractions one by one. So let's go ahead and do that on another sheet of paper so we don't run out of space. But what we're going to do here is simply look at the results and say, hey, how would this calculation be filled in based on the data we just came up with here? So let's do it. For the test stat, the chi-squared test stat, it'll have a bunch of fractions, right, that look like the following. So let's leave that blank for a second. Let's fill it in for the first fraction. For the first one, it would be the observed value, right? Observed value minus the expected value. So it'll be 146 minus 131.61. 131.61. And then divide by that same 131.61. So there it is. That's our first fraction. Observed minus expected squared divided by expected. Plus, then we fill in our second fraction. And how would our second fraction look? It'd look the same way, basically, but it would have 106 minus 102.24, 102.24 squared divided by that same 102.24. Plus, then we would do this one, right? I'm just going to say dot, 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 and then just do the last one for us. The last one would be 292 minus the expected value of 273.85, and then divided by 273.85, right? and that will be approximately equal to, etc. So I've done 1, 2, 3 of those fractions for us. Again, you can do the other 3 and see if you get the same overall test stat result. When I'm done, it works out to be 10.197 approximately. So that's the approximate result. Okay? Alright, good. So now that you have the result for your test stat, what's our next step? Well, our next step, you know, is always to get a critical value, a chi-squared critical value. And to do that, we're going to draw the little curve as a visual aid, right? So we'll draw that kind of highly skewed curve, the long skinny tail on the right. Remember, that's where the rejection region is, right? And it starts off at 0. And so for the critical value, we're essentially looking for what number here starts the critical region off. Well, the chi-squared critical value has a certain pattern or a certain form. It's going to be alpha, right, comma, the number of rows minus 1 times the number of columns minus 1. So that's how we fill in the notation. So what was our alpha in this problem? Well, let's take a look at that real quick. Our alpha in this problem was 1%, right? So this guy will actually be chi-squared 0.01, comma. What were the number of rows? Well, the number of rows were 2. If you take away 1, you just get 1, right? The number of columns were 1, 2, 3. If you take away 1, you get 2. And if you do 1 times 2, you end up with 2. So our critical value for this problem is going to be chi-squared 0.01, comma 2. In other words, we're going to go to the 0.01 column and look up 2 degrees of freedom. Let's go do that right now and figure out what that chi-squared critical value is. Here's our chi-squared table. We're looking at 0.01 with 2 degrees of freedom. That's not on this first page, so we'll go to the second page of the table, and we see that the 0.01 column with 2 degrees of freedom gives us 9.21034, or roughly 9.21. Okay, so the 2 places, our number turns out to be 9.21 for the chi-squared critical value. I'm only using 2 places because I can see it doesn't need to be rounded much further because this number is already clearly beyond that. And so we're going to say, hey, this value here is going to land in our rejection region. And so that means our overall conclusion for the problem is that we should reject HO and therefore support HA, right? And what does that mean here in this particular problem? Well, let's take a look at our HO and HA and see what that tells us here then. Well, looking at our pair of hypotheses that we started with, if we are rejecting this, we're saying the 2 categories are not independent, and if we're supporting the HA, we're saying they are dependent. And what does it mean to be dependent? Well, essentially here we're saying that alcohol consumption and congestive heart failure have something to do with each other, right? It basically means that, you know, there's some connection, something happens when you pair these 2 things together. In other words, it's not just, you know, that drinking is completely unrelated. There's some relationship. And the relationship could be complicated, right? As we know from studies you might have read about, a little bit of alcohol each day is okay. In fact, actually, it may be healthier for you than having no alcohol at all. However, once you exceed a certain amount of alcohol per week, then it might be crossing over into the unhealthy range again. So actually, people say it's kind of like a J pattern, actually. They say the shape of the curve is kind of like this. In other words, you know, if your risk of heart disease here is here if you don't drink at all, if you're an abstainer, and then it drops as you drink a little bit each day. But there's a point where as you start to drink more, you come right back up to where you would be at the abstainer level, and then if you drink too much, your heart disease risk rises. So essentially the idea is that, you know, better to be an abstainer than to be somebody who drinks too much, but better to be a moderate drinker than just an abstainer. That's kind of the idea of it. And that's what we know from modern science. But this table or this result from the chi-squared test just says, hey, these 2 things are somehow related. And we can see that because we're able to reject the claim that they're independent and support the idea that they're dependent.